What weighs more, a kilogram of feathers or a kilogram of iron nails? Of course, the answer is that they have the same weight because they have the same mass, 1 kilogram. Why might one say carelessly a kilogram of iron nails? Because nails are denser than feathers. What I'd like you to do is pause the video and write down the formula for density now. 3, 2, 1. Okay, so there's the formula. Density is mass divided by volume. SI units, mass, kilograms, volume, meters cubed. So the unit of density is kilogram per meter cubed. Of course, if you choose to use units of grams and centimeters cubed, that will give you a density in grams per centimeter cubed. You have to be very careful about keeping track of units. If in doubt, just convert to kilograms meters cubed and kilograms per meter cubed. Here's a list of common densities. You'll notice that air is roughly 1 kilogram per meter cubed, 1.2 kilograms per meter cubed, which might be quite surprising. Water is 1,000 kilograms per meter cubed, a ton per meter cubed. Again, going up, lead and iron higher still. Gold, 19,300 kilograms per meter cubed. The heaviest element is osmium, 22,610 kilograms per meter cubed. And then I've also, just for your interest, included the density of a white dwarf star, nuclear matter, and a neutron star. So densities range from really quite small to really quite big once you get to the level of a neutron star. Interestingly, this equates to approximately a Mount Everest resting on a teaspoon. Just an interesting fact for you there. Okay, without further ado, let's try some of these questions. So you can have a go at as many of these as you want. Pause the video and have a go now. Solutions in 3, 2, 1. Okay, they were really quite fun to do. So they're fairly difficult. It's good practice using standard form and converting between units. Hopefully you can see all those solutions. You'll notice that in red I've sketched out some shortcuts you can take. So you can pause the video and have a look carefully through what I've done. It's unlikely individual calculations would be this involved, although some of these are relatively simple. So pause now and have a quick look through them. Another thing we can discuss quickly about density is how to measure the density of an object. So a regular object, like a cube, so you could measure the dimensions of the sides and then find the volume using an equation. So for a cube, it's very simple, length times breadth times height. You could use a ruler, you could use a vernier caliper, or if it was a very smaller object, you might want, or if you wanted to measure to the nearest hundredth of a millimetre, you might use a micrometer. Anyway, you could then use a formula. For irregular objects, the best thing to do is to fill a measuring cylinder with water and then fully submerge the object of interest if it's an irregular object. So fully submerge it. The water level will go up. So you can measure the initial and final volumes, and then the difference between the volumes, so V final minus V initial, will give you the volume of the irregular object. You can then use a balance or electronic scale to measure the mass of the object, then use density as mass over volume to calculate the density of the object. Okay, so that's called the displacement method. Okay, onto pressure. So these two pictures illustrate the concept of pressure. So these are snowshoes. Increase the area of contact between one's feet and snow and stop you sinking in by reducing the pressure. This is a drawing pin. Obviously, you couldn't push your thumb into a wall. You'd have difficulty, I think. But a drawing pin you can push into the wall because the low surface area of the point increases the pressure that's exerted. So the definition of pressure, the general definition, is something that you should know. Have a go at writing it down with units now. Answer in 3, 2, 1. Okay, so pressure is force divided by area, and the unit if you have a force in newtons and an area in meters squared, is the Newton per meter squared. So it tells us how much force is applied for every meter squared of area, and that's called a Pascal. So a Pascal is simply a Newton per meter squared. Let's try some problems using this equation. So have a go at these two. Pause the video and have a go at these now. Answers in 3, 2, 1. Okay, there are the answers. Notice for this second question, I've been very careful to convert all the distances into meters before I've worked out the volume, just to get everything in meters cubed to start with. The mass I've worked out using density as mass divided by volume, rearranged. I've then found the weight, because what we want is not the mass, but we want the force acting downwards, which is the weight of the block. The question asks for the minimum pressure and the maximum pressure. So you want to think, on which face will we get maximum or minimum pressure? And that depends on the area. So for minimum pressure, I should say, we want to have the largest possible area, which would be this shaded face, 4 centimetres multiplied by 5 centimetres. For the maximum pressure, we want to minimise the area that the block's resting on, and the smallest side is the 3 times 4 side, which is that. So that's why I've worked out these different areas, right? Because you can put the block down on one of 3 sizes of face. So have a look through my working and make sure you're happy with it. The final thing we need to do is look at pressure in liquids. Have a look at this question to start with. So read through that and think what the answer is, A, B or C. So the idea is we've got 2 lakes. One is shallower but has an indefinite extent. It might be several miles wide or long. And then we've got this lake which is deeper, but you can see that it's going to end here. So which dam has to be stronger and why? Have you thought? The answer is A, the Sierra Light and Power Dam must be strongest, so this one, because the pressure that it has to withstand is related to the depth of the water. Right, the water in this lake on the left is shallower, so although there's more water potentially in total if this lake continues indefinitely or for a long distance, the pressure down here will be less than the pressure at the bottom of here. So even though this lake has less water in total, it will experience less pressure. Now the formula for pressure in a liquid is depth times density times gravitational field strength. And what that tells us is that for a given liquid with a fixed density on Earth, usually, where we have a fixed gravitational field strength, 10 newtons per kilogram, the pressure difference, or the pressure due to the liquid, is only a factor of the depth, not the shape of the container or anything like that, simply the depth. Let me just come back to this situation for a minute. So look at this, and particularly this on the left. So if you're not convinced by my previous argument, let's take this left-hand situation and let's make it more extreme. So imagine I had a foot deep body of water, okay, only a foot, so like, ankle depth, a bit higher, and imagine it extended for, let's go 10 kilometers, right, or 100 kilometers even. Hopefully you can see intuitively that this piece of wall here wouldn't have to be particularly strong to hold back just a foot depth of water, even though with this length of body of water, you could have, many, many tons of water within this 1 foot layer if it extended for a long distance. So that wouldn't affect, however, how strong this had to be. One thing quickly, remember units, we're still working in pascals, it's a pressure, depth has to be in meters, density has to be in kilograms per meter cubed, and the gravitational field strength has to be in newtons per kilogram in order for the units to work out. Okay, let's try an exam question. So, have a go at this question using the equation we've just outlined. Pause the video and have a go now. Answers in 3, 2, 1. Okay, there are the solutions. Let's just look at this situation. This is called a barometer, a very simple barometer. What's holding this mercury column, all this mercury up, by the way, is the pressure, atmospheric pressure pushing down on the mercury here. Okay, so it's kind of balanced, right? We've got an equilibrium situation. If this pressure goes down, so if these arrows, if I can rub them out, make them smaller, if the pressure goes down, then this height is going to reduce. And therefore, the column of mercury won't be able to be as high as it was originally. One final little problem. You may have seen these before. This is Pascal's vases. So I'm going to fill this with water. So imagine pouring water into here. Which of the following situations is going to actually be the case and why? So pause the video and think. The answer in 3, 2, 1. The answer is C. Again, because pressure only depends on the depth for a given density and given gravitational field strength, the water will fill these jars, ignoring the fact that there's a gap in this one. So imagine it was sealed, will rise such that the depths are all the same, irrespective of the shape of these of this glassware. There is one very final point I'd like to say, and that is that in a liquid or in a gas, so let's draw some water in a container. If I've got an object here, the fluid pressure acts in all directions. Okay, so it doesn't just act downwards; it acts in all directions. So, for instance, say I had a situation where I had a piece of glass like this, only it had holes in it. And then I had some kind of plunger, and this was filled with water. If I push this inwards, what would happen is the water would fire out or spurt out in all directions. So that shows that pressure in a liquid, because the particles are dynamic and they can move around each other, apply force to each other, pressure acts in all directions, which is the final point, in fact, on this list of syllabus statements. Hopefully that's been useful. Thank you very much.